For decades, humans have looked up at the night sky and imagined leaving our solar system. We dream of boarding an interstellar ship, traveling across the galaxy, and finally stepping foot onto the welcoming, solid ground of a distant, Earth-like exoplanet. But the astronomical reality is far less accommodating. The vast majority of the universe is a graveyard of intensely hostile and violent environments. Most planets discovered by our telescopes are entirely incompatible with human biology. We are dropping a physical, first-person landing simulation into the coordinates of 5 of the most extreme exoplanets ever discovered. Translating that distant telescope data into a physical, boots-on-the-ground experience reveals exactly how rare, fragile, and incredibly lucky our conditions on Earth truly are. This animated diagram illustrates the grim fate of our first target, WASP-12b, which is undergoing a process called tidal stripping. This is a destructive phenomenon where a planet orbits so closely to its host star that the star's immense gravity physically tears the planet's atmosphere and mass away. Because of this proximity, the ambient temperature reaches a staggering 2,500 degrees Celsius. These temperatures would melt a spacecraft's hull down to slag before a landing sequence could even be initiated. Even if we manage to deploy a lander, dropping onto a slightly cooler planet like 55 Cancri E offers no relief. If an astronaut reached the surface, they would find zero solid ground. Instead, they would plummet into vast, turbulent oceans of boiling lava, battered by molten rock storms. At 2,000 degrees Celsius, immediate physiological failure is unavoidable. A heavy, industrial-grade spacesuit would fail in mere seconds as the water content inside the human body rapidly evaporates. Extreme proximity to a host star makes planetary survival mathematically impossible. Intense heat and crushing stellar gravity stand as the ultimate cosmic barriers to human exploration. Moving deeper into space, we approach HD 189733b. From millions of miles away, it is a stunning, deep blue sphere. It is entirely reasonable for an observer to assume that color indicates calm, Earth-like oceans of liquid water. The atmosphere is a chaotic engine of 7,000 km/h winds. These supersonic currents whip around the planet, carrying debris and gas at speeds that would instantly destroy any human-made structure. Under immense pressure, silicate particles in that atmosphere melt and fuse. This creates horizontal rain made entirely of high-speed molten glass. Any explorer caught on the surface would have their suit instantly shredded by the barrage. A planet's visual similarity to Earth guarantees absolutely nothing about its surface survivability. In the vastness of space, beauty is often lethal. Next, we submerge into K2-18b, a massive world scientists classify as a Hycean planet. A Hycean planet is a theoretical type of world characterized by a thick, hydrogen-rich atmosphere covering a massive global liquid water ocean. This diagram illustrates the crushing physical reality of landing there. K2-18b has roughly 8 times the mass of Earth. That massive downward gravitational force would make every single bodily movement agonizingly heavy, exhausting an explorer almost immediately. To make matters worse, that thick, hydrogen-rich atmosphere is entirely unbreathable. An astronaut would be permanently trapped inside their heavy suit, unable to take a single breath of the local air. But beneath that toxic air lies the global liquid water ocean. If that water is chemically stable, it theoretically harbors the exact conditions required for alien microbial ecosystems to thrive. A planetary environment that is entirely toxic and physically crushing to human biology might simultaneously serve as the galaxy's most highly optimized incubator for alien life. Finally, we arrive at TRAPPIST-1e. This world is remarkably close to Earth in physical size, features solid rocky terrain, and orbits perfectly within its star's habitable zone. The habitable zone is the specific orbital distance where temperatures allow liquid water to pool on a planet's surface. In our simulation, an astronaut steps out onto solid, stable ground with familiar density. There is no boiling lava, no glass rain, and no immediate atmospheric threat. But there is a fatal flaw. The host star is a red dwarf. A red dwarf is a small, relatively cool star that frequently erupts with powerful, unpredictable bursts of radiation. Without warning, it unleashes massive, highly radioactive stellar flares directly at the planet's exposed surface. Finding the perfect rocky landscape with liquid water is useless if the host star constantly bathes the surface in unshielded, lethal radiation. Pulling back from these simulations shows that the vast majority of worlds we've mapped are hostile to every biological process we understand. But mapping these extremes, the boiling lava, the sideways glass rain, the crushing gravity, and the sudden bursts of radiation is actually a crucial scientific exercise. By understanding these precise lethal variables, astrophysicists can strictly narrow their search parameters. They can systematically rule out deadly systems and focus their time and resources on truly viable planetary candidates. By observing how variables like stellar flares or silicate rain affect planetary stability, we can filter out billions of candidates. This process of elimination is our most effective tool for locating the few worlds where the chemical and physical indicators finally align with our own. Every extreme world we map brings us closer to a planet where we can finally take a breath.